We want cloud.
There we go.
There we go. Now it looks like it's recording.
Recording in progress.
All I gave you?
Huh? These?
No, the cloud version, because normally.
Oh, yeah. It's the club has it, yeah. The club-
Normally you don't have the cloud version. But
Yeah, no, it's.
I'm gonna guess.
But then I end up downloading it anyway. Yeah, so introduction, I'm Matthew, KM6WRU, as many of you know, I'm Dylan.
Hi, Matthew.
I'm Ryan, KM6REG.
Ryan.
And so first meeting for the quarter, thanks for coming. We're gonna be talking about the antenna design contest we're running this quarter. Hopefully it goes well. Those. I got inspired, I was looking through the club drive and someone about 11 years ago now, Kenneth Bennigan ran the same very similar design contest in 2013 for 2.4 gigahertz of Wi-Fi. And I thought it was really cool. So let's find out. It was kind of failed to do. Only one person actually submitted it. So
If you're watching this, Kenneth, no harm, no foul.
Thank you, Kenneth. But hopefully it goes better this time. So this is a, hopefully should be pretty accessible to people.
So do you want to move the?
See, this is just gonna be the problem. We have to move it the entire time.
Michael's the blocking over.
No. We have to help him with the mouth.
I can't see. Yes.
Wait, Michael, go move.
Well, if we do that, then it won't record you to it, or will it?
It will,
It's fine.
It's not recorded YouTube.
It doesn't?
Yeah. No, that's like you put it there just small.
Your face needs to be.
Yes, it helps.
It's weird. It's useless.
Yeah. That's wonderful.
Okay, there you go. Yeah, so basic contest setup. So we're gonna be building 5 gigahertz directional antennas, basically as much gain as you can get. Trying to do a point-to-point link from on campus. Current probable test site is the CPARC structure. So there's a line of sight up to our Arden installation at Clark Valley. So the other side's already installed. Find some there, but the goal is to be building custom antennas for that and see how much data throughput you can actually get. So contest rules, we're going to be measuring your real world performance with a performance testing tool called iPerf. They will be tested using Ubiquiti Rocket 5 radio and that's the piece. Flash with custom Arden firmware. Lets them do unencrypted communication on hand bands. So we'll talk about it a little bit later. What Arden is. So we're going to be using channels 170, 174, 176, 178, which corresponds to 58, 55 megahertz and 58, 95 megahertz. That's the range you should tune in your antenna for. So Matthew will talk about this more in the design section. But when you're designing antennas, they have certain bandwidths, so you should target around there. There's actually this online for different designs to get started. So those are the kind of things you punch in, and then either testing, with asking anybody for help. You can test on a network analyzer what the frequency response is, and around there should be what you should be doing. Something very interesting about Arden is it is actually MIMO, so sort of multi-input, multi-output, but it actually needs to be built to antenna or one antenna that can be fed right at 90-degree polarization offset. So if you build a single linear polarized antenna, which is really standard, you take another one and mount it, rotate it by 90 degrees to get both extremes. Arden actually uses both of these to do really cool fancy stuff to make your link better. It makes it faster and also even more power for the same. So you can be feeding with 2 SMA connectors. We will provide adapters that go from here to cables to 2 identical cables to plug into whatever antenna you provide. So what's MIMO? I'm assuming most people have never heard of it. So up there we have CISO. This is standard single input, single output, just antenna to antenna, with only one transceiver chain. Right, so inside of each of these, there's a transmitter and receiver. They can talk back and forth. With MIMO, more advanced concept. Don't really do that in a lot of radio stuff, but with digital radios, you can split your signal into two separate chains, transmitting two different digital data streams, and then recombine them on the other end. Basically double the data rate, but you can also do other cool DSP stuff that goes way into the head. But basically, you can build a single antenna and connect it with the emo system, but it's a really bad idea. So we strongly encourage everybody to design an emo antenna or to make two CPARC antennas. So short primer on Arden. This is the system we're going to be using for testing and integrating with. This is why we're building the antennas, because we administer the Arden mesh, or a couple of nodes in the Arden mesh system around the county. So we have one on the tower there. So we have one out here at Clark Valley. This is out overlooks Moore Bay from the south, where we're going to be connecting to, that we administer. And then I believe we also help with the one on Cuesta Peak. There's one on Cuesta and Tass further up. We helped install the system in Paso. So we've been, it's been an ongoing project around the club for a couple of years now. It's pretty cool. So basically the 5.8 gigahertz Wi-Fi band happens to overlap perfectly with the amateur radio 5 gigahertz band. So we can basically ignore the other regulations for Part 15 and apply Part 97 rules to use the same technology. That means we have to follow all the same amateur radio rules, but we can use frequency or channels that aren't allowed in the normal regulations, like 174 or 174, 176, 178.
180, I think, too.
And 180 are all licensed only or indoor use only, designated under Part 15. But if we follow the amateur radio rules, like don't use encryption and don't go over a certain speed limit, I think there's bandwidth on that. It's limited to 20. 1.6. Yeah, it's a lot. But
So
basically,
like how often for 2048?
you follow all the amateur radio rules, and you can pump the power out of 2. 1.5 kilowatts.
1.5 kilowatts.
Isotropic radiated power magnets, or peak emitter, which means you can really get really long distance links.
But why don't we?
But and that costs a lot of money. So what we mostly do is we take off the shelf hardware like this and flash custom firmware on it that lets us do unencrypted 802.11 with our call signs on ham bands. You can get way faster data rates than what you get with traditional packet radio on lower frequencies. We can do fun stuff like host cameras. So this is a picture of our Clark Valley install. So we have one camera here that overlooks Morro Bay and a couple other cameras around the county that's all viewed over the mesh, all transmitted with branch radio. And it's all on the website posted on a little Intel Dell Wise computer sitting up in the vault. Over the mesh, yeah, and actually forwarded to the so that's why we're doing this. It's hopefully gonna be lots of fun. Oh yeah, here's a sign up form if you're interested. Scan that or type that in. There's a place to put down the email where I'm just email out more competition details. I have a flyer. I think we're going to show that at the end after Nazis with more detailed competition rules and any updates we'll email it to anybody without this.
I was going to mention when the contest was.
I didn't mention that.
It's a couple
fight back. Yeah.
Yeah.
It's on here.
Wrong one.
Contest rules.
Yeah, so. All right, a couple things I didn't mention. Teams are welcome. I think Matthew said somebody asked. Anything to make it easier. I know in the past, I think there was a regulation last time this was posted. There was also a budget regulation. I mean, it's up to you, any budget. Basically, we want to encourage more participation. It's supposed to be as open as possible. Teams of any size, just one person, up to as many people as you want. And then we are gonna be testing tentatively, probably not gonna change Saturday, March 2nd, which is the week. Saturday after week 9, before week 10. So hopefully before people are too busy with finals and after people are done with finals. Hopefully it's the last free week in the quarter, so. Maybe people will be free then. If it has to change, we'll move it. You can possibly push it to finals or. Everybody who has little attendance system. And then similarly, I think I mentioned it on the slide before, we're probably going to be testing them from the executive to parking structure. On the top of there, you can actually see line of sight straight to Park Valley. And that's easier than typing up speed with all that. There's only a couple places on campus where you can actually see them. That's the current tentative plan, but again, any updates we got in this.
Okay,
And then I'll automatically take over and talk about who's on.
yeah, so we're gonna talk a bit about antenna design, just ideas and how to and stuff like that. Hopefully it's not too intense, we'll see. Yeah, I'm not gonna cover like a lot of the stuff that we cover in the class, like propagation, boundary conditions, far field, or kind of how waves actually detach from the antennas, which is a cool thing if you look it up. I always forget. That's Speak for yourself. Yes, over here. Okay, so pretty pictures. These are my slides. Get used to them. So just for some basic topics, isotropic radiator. That's like a point source, right? And it radiates spherically, uniformly in all directions. So you just imagine a sphere, but that's not real. So kind of the close fun fact. We wish it were, or we wish it was. What you can get though is omnidirectional, which is this fun looking donut, and that's the pattern in 2D. I always forget this side leads azimuth. This is like elevation plane, or I might have it mixed up. Essentially, your wire's coming out that way, you're putting power in that way. So there's nothing going to be transmitted in that one direction. However, everywhere around it, there is RF energy being transmitted. So that's good. Another quick thing, standing wave ratio. So that's kind of like the impedance match thing, resistance, but like with complex stuff associated with it that I don't want to get into right now. That is very important and frequency dependent. And yeah, just ratio of power transmitted to that being wasted, kind of being reflected back towards your transmit. So ideally your SWR of 1 is like perfect. That's all power being transmitted, nothing being reflected back to you. What do I got next? Beam width. So that's kind of your half power points on the antenna, the directivity of it. So you want it to be directive in some cases, like our case, right, where we have 2 endpoints and we want to point at each other. So there's going to be half power 3 dB points on this, and essentially that's what we call your beam width. So that's the main beam there, which pretty intuitive if you look at it. So there's your beam, maybe like 30 degrees, half power beam width. Last thing I got on here at least is bandwidth. So the frequency range of that best performance might be covered up. I don't know if I put it on here. I did. So essentially that resonance there is where the least amount of power is going to be reflected back to it, what we call S11 essentially, or the reflection coefficient. And that is, yeah, where you want to be. So typically use something like minus 10 dB or minus 20 dB to characterize that. All right. Like I said, I'm sorry, but get used to them. Polarization consideration. So like Brian talked about, essentially we have dual polarized, well, fancy word for y'all. Dual polarized linear orthogonal modes, essentially. Fancy, right? So essentially we have these linear modes, right? But we're gonna have 2, one that's at 0 degrees, so vertical, and one that's at horizontal polarization. So let's say 90 degrees for this case. So then you can also do that with minus 45 and 45 degrees, which would be called like slant polarization, like we kind of see here. They're slanted to minus 45 and then plus 45 on one of them, I believe. But yeah, So that's kind of what that is. So here's an example from inside of a station. We have two feed points, one that's doing vertical and one that's feeding it horizontal polarization. Yes, and what that allows you to do, like we were talking about earlier, is two essentially separate data channels. Or I guess not channels, it's like
30 dB.
30 dB, you want
Even though
to
they're
be,
on the exact same frequency, it acts like two separate isolated channels. By like 30 dB, that's like 1,000 times less power
something like that, yeah.
on one channel. Or that leads to.
And so that's what's known usually as cross polarization, as antenna people know. And yeah, that's good to have. So you can also have circular and elliptical polarization, where you're yeah, elliptical polarization is one or something like that, or your axial ratio is one here. So that just has to do with the major and minor axes, but forget I said that, that's not important for this. And then here's how you'd actually feed something with a circular polarization if you're curious. You either cut off the edges, or you feed in two inputs 90-degree out of phase. But that also is kind of extraneous info, just kind of for those that are curious. So potential antenna designs. We aren't talking about dipoles here because we're trying to do directional stuff, like I was saying. So stuff like a patch antenna, a microstrip patch antenna, something like a patch array or a sector antenna, like what I was showing before. Something like a Yagi Uda. We always say Yagi Uda. We never say Yagi for everyone out there. For the record.
Explain why.
Why?
Yeah.
Really quickly. 1922, I believe, they came out with a paper. Yagi was the, I believe, advisor, and he translated Uda's paper from Japanese to English. But everyone essentially just calls it a Yagi, but Uda is the one who actually came up with the design. So,
That's.
yeah, that's shoes, yeah. So
And his
he-
advisor was the color credit, basically.
So this one guy, who's really smart, Constantine A. Balanis, essentially in his book and a lot of books, essentially, they're like, yeah, no, give Uda some credit here, so. They're called the Uda Yagi antenna, but that's like confusing, yeah, that's like using the metric system in the US, it's never gonna happen. Yeah. Alright, so here's another fun one, a log periodic. I'll talk about it a little bit later, but I'm not super familiar with them. But the idea is that you can kind of have a very wide bandwidth on that because you have different, essentially dipoles, but they're directional, right? That are all fed essentially at the same time. We'll kind of see it later. And we got parabolic reflectors or dishes, as the cool kids call them. You have an LNB here, a low noise block.
Those are low res lockdown.
There we go. Yeah,
It's
so
usually used for more high micro stuff.
we aren't gonna touch
You
that.
don't wanna touch that.
But it has an amplifier inside, filtering and mixers and stuff like that.
If you wanted to build a,
A-band or A-unit.
well, if you wanna build a parabolic input for this, you could, just don't do an LNB, do another kind of feed one that doesn't have frequency.
And so here's patch array, kind of like what I was talking about, phased array, so you can control the beam. You wouldn't really need that for this, but you could do a patch array, which will improve your performance or your gain. Oh, that's one other thing I should mention. Not sure if it's fairly obvious, but when you improve your gain, you decrease your beam width, so it gets harder to point your antenna. You have to be a lot more precise with it, so. There is a downside, it's not just like, oh, I can just increase gain infinitely.
Also get weird side lobes. Sometimes.
That has to do with other things, like antenna spacing and stuff like that. Oh, yeah, I'll come back to me here. So antenna design software, Maxwell's equations, how many of you seen this in like physics 3? Yeah, what is it, the integral over del V equals 0, the integrated flux in a loop is 0 or something like that? I'm terrible with these, not gonna lie. But you know what isn't? Software, because people are smart. So there are all sorts of things called like boundary conditions and stuff like that when you have two different interfaces, right? Fields perform or do things in a specific way, and that's what these solve. So there are a couple. The main one I recommend is HFSS, high frequency something stimulator, something like that. free for students, so that is nice. So you can download it. I think I have a link somewhere in there later, but not super important. Pretty easy to find. But it's
Normally a really, really expensive piece of software.
yeah. There are other free ones though, like Forneck 2.
So if you have holding all your fans.
Mhm.
What's the name of something?
HFSS. It's one of the few up there. It's the first one I believe I got. Second bullet point. Yeah. Or first. It's the same difference.
If you get the student version of HFSS, there's a limited mesh size, so if you get,
It's not as bad as it used
okay, but if you get super crazy with your antenna design, it won't handle
to.
it.
Yes.
Stupid.
Which to resolve that, you can use the virtual lab, right? Yeah, so we have like virtual labs.
Microwave one also has.
Yeah. I forget what it's called, like software access anywhere, I believe. You can look at the IPS portal.
There we go.
Or if you don't want to download it, it's like 8 or 9 gigabytes for your computer, so it's up to you, but you can access it via OneDrive and stuff like that, so. That's another option on a virtual machine running it. You don't have to kill your RAM or whatever the kids say these days. Yeah, so analytical methods of solving Maxwell's equations. So that's what these essentially do. So there are a couple of different ones. I just wanted to highlight on them because they're really cool. Trust me, I don't understand them. Far smarter people implemented them.
Bah.
Finite element method, FEM. The domain of the problem is discretized into small elements. So you see here kind of meshes and Maxwell will solve for each one of those smaller meshes iteratively. Then we got method of moments, projection of an integral equation into a system of linear equations by the application of appropriate boundary conditions. They're all fairly similar, at least in this basic wording, but they all have their pros and cons kind of deal. The only big one that caught my eye was FDTD, finite difference of time domain. And it solves Maxwell's equation directly without any physical approximation. So like if you need precision, that's it. But that's gonna cost you a lot of time. So yeah, kind of some more arrays and like I was saying, the mesh sizes. Okay, more obscure antenna designs. I thought that would be kind of fun. I was looking into some. So we got the biquad down the bottom here. Looks like two kind of rhombuses. You can also do like double and quadruple biquads, along with having 3 or 4 or 4 or 6 of them or whatever, and creating a similar, like we were talking about earlier, omnidirectional design. If you want like a better Wi-Fi antenna for a router or something like that. We got all sorts of weird stuff like fractals. So the only real benefit that I understand to these is that they're like frequency independent, essentially, which pretty cool when you come to think about it, to an extent. Like if you're going to terahertz, that's not gonna work for you. Probably even above like let's say like 50 gigs, like not sure how well fractals do. And then another fun one I looked into was what's the one I didn't cover on there? Oh, Franklin Co. Okay, well you can see my slides. Franklin antenna. So that's kind of this one here. And I believe what I meant to say was like these co-phased elements. You can look into it more, but it's these little dips that prevently are like RF traps, I believe, if I'm not mistaken. Which those are also fairly directional. They're like 9 dBi. When we have dBi, that's like decibels relative to an isotropic radiator. Okay. Cool. Here's where it gets a little in depth. We'll see. I might just brush over this quickly. So yeah, there's transverse electromagnetic waves, right? We have fun board time here.
Oh, I guess not. I guess not. Oh, whoa.
Okay, I can't draw well in 3D for the record.
Dang.
Okay, so we'll call that your E plane or your E field.
You playing?
Field. And your H plane is going to be orthogonal to that. And so we call that TE, transverse electromagnetic waves. But that's not the case for all antennas. So for patch antennas, so where this is your substrate or dielectric material, which in other words is non-conductive, and then here's your actual copper on top, you're only going to get transverse magnetic waves. And that's due to all sorts of boundary condition stuff. And the math's really cool, but painful if you have to do it for a class. And Yes. The first mode is preferable. Just because otherwise you get weird like bunny ears or different side lobes, you don't get a single main lobe. So you kind of want to focus on that because otherwise you'll have issues, you know. Not all of your power might be transmitted, it'll be transferred, having two lobes, which usually isn't desirable. Usually. This will be important later, I promise. Oh, there we go, I got rid of the bar. Cool. Alright, feeding methods, so here's just some examples here. You got like kind of edge fed method, where this is the quarter wave transformer, which just transfers 50 ohm impedance here, which is, you know, if you haven't heard 50 ohm, where have you been? Well, 50 ohms essentially is just what we use for almost everything RF. It's something to do with the geometric mean of 75 and 33. There are meanings to both those somewhere. But that's outside the scope of this. So that quarter wave transformer transfers the impedance of that 50 ohm that's desired to the path impedance at the edge here, which typically is around 200 to 300 ohms or so. Then, if we can move this out of the way, we have coax line feed, which also this has to come back to polarization, right? When you're feeding it this way, I believe it's H pole because it'd be in the horizontal plane. Whereas if you're feeding it with a that's not coax line feed, you're feeding a D pole, so vertical polarization. How you switch that? Just literally tilt it 90 degrees. It's not that complicated when you think about it, which is what we're gonna end up doing. So if you design, for example, two edge feed microsircuit patches, we're just gonna flip one. And hopefully it should work. Worst case, we just throw it in the anechoic case and have some fun. Which is in the other room, which if you aren't familiar with, it's just a device that we hook up to a VNA and we vector network analyzer to measure the antenna properties and characteristics of it. So that's a fun one. We have like aperture and essentially coupled filters or feed methods that you can do. Those are a lot less common just because they're more complicated and typically harder, like strip line methods. And then here's my favorite, of course, the inset fed. So it's essentially the same as the edge feed, but you don't need that quarter wave transfer because we're feeding it further in at a point where we're trying to get 50 ohms instead of the edge, which is 200 to 300 ohms. And so our patch is good. They're good enough. So in you know simulating you get 10 dBi of gain, but in reality you maybe get 6 to 8 dBi. So that's why you probably want to use an array if you go with this approach. All right, we're almost to the fun stuff, I swear. It's more pretty pictures and less me talking, hopefully. So yeah, creating one. How? We'll get there. Start with calculators. So essentially there are a whole bunch online. There are also equations that are fairly straightforward to follow that the calculators typically have on them for calculating this line length. So this we also want to be 50 ohms here, this piece. And then for this inset length, along with the spacing to the actual patch itself, along with the patch length and patch width. So we can get all that using an online calculator. So that's good. Then we use optometrics in HFSS, which I'll show in a little bit here, to essentially parametrically sweep through specific parameters, as a parametric sweep does. And then physical materials that are on here that apply to the properties essentially. The substrate dielectric, so what's underneath it, what we talked about, what's insulating. The permittivity of that dielectric, the loss tangent of that dielectric, and then the copper thickness. So typically you can have 1/2 ounce or 1 ounce copper, I believe, which corresponds to a specific dimension, along with there's all sorts of other crazy stuff, like copper roughness and stuff, but that's insane. Yeah, and then patch dimensions are also very important. So this is just the inverted F microsircuit patch antenna that I thought was cool, because we've all seen, or most of us have probably seen ESP32s. But yeah, just a fun little inverted F. Do I know how it works? No, but I thought it was cool to put in there and stuff. And here's like a little UFL connector as well. All right. So here is essentially a table to design a Yagi-Uda antenna. There are a whole bunch of different things that go into it, like needing balance and stuff like that. That's a folded dipole feed. The only thing I really want to get into, although I spent all this time working on this, is, you know, you got a driven element, you got a reflector, and you got directors. So the folded dipole up there is your driven element. That's the only thing connected to the radio via coax line. You have your reflector, that's the element behind it. And then you have all these directors in front of it. And you can have varying amounts of directors, and each one will typically add about 1 dB of gain. And then the reflector behind it adds about 5 dB. And essentially, that reflector is cool because it's a bit longer than what's required to be resonant for that frequency. So then essentially it bounces back RF or propagates in the other direction. And the directors are capacitive. So inductive is kind of longer than resonant, capacitive shorter. All the directors are shorter, capacitive. So they direct the RF energy straight forward. So you get a nice looking beam. And typically you get like 10 to 12, I want to say dBi. You can probably get more honestly, but and then you use some chart parameters. There are a lot of other things to look into, but they aren't super important, honestly. But the main thing is the spacing is consistent for those, and then the lengths as well for all the directors.
These are like fun experimental, right?
Yeah, so these are all experimentally determined. Yeah, that's the only thing I can say. Other antenna design methods, yeah, so parabolic reflectors, dishes. It's kind of fun. You got Cassegrain and Gregorian. There we go. Feed. It just has to do with the actual orientation of your feed antenna. Then you got other fun things like reflect arrays here. So those are all microstrip patch elements that we talked about earlier. They're literally squares on there, but they act as if they're concave or convex or whatever the term is. So I believe they use these a lot of times in satellites to get super high gains because you can't really put a dish up in scale, but they have. And they will. Yeah, got Voyager, rest in peace. Kind of. But yeah, so I'm pretty sure they're used pretty common. Along with, we have a professor at this school who has written a book on it and stuff like that. So it's kind of cool. He knows a lot about them. And then we also have log periodic design, like I talked about. Both sides are fed, and you have your dipole elements that kind of, I don't know how to say, create a funnel almost. It looks like it makes sense, and it does. I'm not sure beyond that.
Fed by the beam.
Yeah, there's research you can do. There are materials out there for all of these, so it's pretty nice. All right, this will be pretty quick. These are pretty pictures I was doing. So yeah, we have a software called HFSS, like we were talking about, high frequency something simulator, structure simulator. There we go. Hey. Yeah, so you think you need to make all these by hand, right? Wrong. They have them built into the software. However, you know, you will need to do optimizing of it and, you know, perform some parameters via equations, but
Software good, but other than hospital things?
somewhat, it'll simulate it. You're still gonna have to produce it. Yeah, so there it is.
Well, five CPM time.
But yeah, so you press view, ACT extension, launch wizard, antenna toolkit. And then, yeah, so here's some of the parameters for the quick and easy design I did. So I did just a basic inset microstrip patch antenna that we were just talking about. 1 ounce copper, 62 mil substrate height. I picked this substrate. So Rogers also gives out free substrates for students. So you can get the substrate and essentially mill it somewhere. I just found IEEE has a mill. It's kind of small, and then I think Innovation Sandbox has a mill, but yeah, we'll see. We'll see how that can get done. Yeah, 50 ohm feed line, and then pressing synthesize will actually produce the required dimensions. So I also use the equations, but yes. this is something that I wanted to show, but I cannot. So once you simulate one of these, you can create an array of them pretty easily using something essentially called a unit cell. And it just does basic multiplication on the pattern produced by one array. And then the other cool thing is, I didn't have it on here, but you can view the patterns pretty easily on HFSS of the entire array, so. Overlaid on your model. So here's my cute little inset fed microstrip patch antenna. So like we were talking about earlier, you have the transverse magnetic propagation mode. So you can see at the edge here of the length that we have propagation occurring through the antenna. Another thing that's important is scaling this down. Originally, it was just entirely blue. I could probably use some more work on here, honestly, but scaling that E field vector down will help with that, so you can actually view the fields. Yes, right click on that. That'll do it. And then also you can right click, I believe I'm showing it up here. On the, so that's a solid body that was produced. They just called it patch antenna. Right click on it, you can scroll down to, I believe it says something or show fields or something like that. And then you have your choice of the E fields, H fields, or magnetic fields. We're mostly going to want to look at E fields. Yes. Here's the fun one. Okay, so there's the basic pattern of that previous patch. We got about, maybe read it, but it says 8.15, 8.17 dB. So not bad for just a basic design that just kind of got thrown in there. You can press on, I have it on the previous screen. There's blue above here. That tells you your model name, or is kind of the HFSS workspace. And then you can see all the variables, which is very nice because they automatically produce this with that synthesis button. And then you can go in a second and use some optometrics. There we go, that's the word. To essentially sweep through value. So I think I said, what is it? 6 inset distances and 4 inset gap distances, just as a reminder. This is the inset distance, this is the gap distance. And then I got out this output for gain. AJ saw that earlier. And yeah, this helps more for things like, yeah, you probably don't want to do 28 combinations, to be honest.
Yep.
Or 24, I can't do math. You know how math works. But it's a nice way to kind of view how different parameters will affect your models. And you can kind of go through them and be like, oh, going this way wasn't really helping me out. I'm going to narrow down the scope and go the other way with my values for my inset feed. So that's typically used for like SWR and stuff like that. And then maybe, well, you wouldn't want to look at the 3D radiation pattern because that would get crazy. Yeah, the final thing I didn't have time to do, but typically you take that design, you'd export it as a DXF, which I don't stand for sometimes. And you import that into Altium or something like that. You get out a Gerber file where you get your different layers, and then you can typically mill it out or send it to a manufacturer to get produced. So here's just some random ones I found online. But I've done similar looking to that, minus the circularly polarized one, that whatever the heck that is. Yeah, it's a good idea to check it before you send it in on a third party, because Altium can sometimes be a little silly. You can also use KiCad, that's another free one. So I should mention really quickly, Altium 2 is super expensive, but for students it's free, so that's nice. And they use it all the time in the industry. KiCad is more.
KiCad's free, it's open source, and we use it.
Not awesome.
Yes,
Yeah.
More for like tinkers, I'd say, but like it has a lot of features that are way easier.
If you just look at really big projects, it's really cool tools that KiCad's just.
Like for example,
KiCad's full of feeds.
yeah, for example, like setting that 50 ohm microstrip feed that I was talking about earlier. This guy here, it's really easy to do in KiCad. Altium, you have to like set like parameters, set rules for that, and then it didn't even work for me, so that was great. So yeah, KiCad shout out there. I think that's all I had. Oh yeah. Beautiful slide, right? But yeah, I can help you get started with the software. It's pretty easy to find online.
So you know, how can I look at these slides?
I'll send it out.
The Discord.
And also the PDF I made with all the.
Yeah, so we can go into that real quick. That's the end of the presentation side of things. Okay.
Yeah, thank you, Matthew.
Thank you, Chris. You're my feeder, you know? My
I'm your
savior.
feeder. Whoa,
I love how this is getting recorded too.
I'm your feed.
You're my
Yeah,
feeder.
yeah.
You can feed me the M5 Titanium.
My dish.
So, really quickly, here's more detailed rules. It's all good. You think you'll have all the information anyone needs. If I missed anything in the talk or the slides, this will be going out to anybody who filled out the form and also on the Discord. So, or it'll also get sent out in the Discord and the announcements channel. I'm also gonna send this to Chuck and Dr. Dolan or Dr. Darrison. And the whole department, and it might go out in the newsletter, hopefully, we'll see who will actually want to do. Yeah, Dr. Darrison, Chuck, Dr. Conley. Who else? Anybody else? Oh, yeah, you're in the.
And then we were talking about a prize, we'll see. Otherwise, you know, so
It's definitely CPARC shirt, maybe you'll get your name on something that we're using for art and county stuff.
put on
Maybe
your
you
resume.
don't want your name on it, we'll have a prize, there will be a prize,
There will be a price for figuring that out.
definitely CPARC stickers too.
Steeper stickers, steeper shirt.
Did they give and you and each one?
Great antenna, maybe.
Watching on YouTube, we're always open for
Sponsorships.
Sponsorships. Yesu icon, if you're out there watching this, anytime.
Yes. Anytime they give.
There we go.
So.
Give them a rock and a five.
We have enough rock. I could do that. Are these rules gonna change or are they staying the same?
They are like 95%.
Like, they're pretty loose overall.
They're pretty loose, yeah.
Yeah.
Okay, I'll say my loophole in now.
Nice. Buy antenna.
Oh, groups of any size are allowed, so
Yeah.
if we're just all one group, we all get free CPARC.
If everyone wants to work together and make one really good antenna, that's awesome.
Everybody learn.
Yeah, everyone.
It's more than one person.
Yeah,
But it's not one
reflector. So we should specify, what they did essentially was. So pretty cool, they put, I believe, SMA and then made a corner reflector and then put oil over it essentially. It's better than a basic dipole though, so that you typically get with your router that just flips up. So it's better than a wire. Okay,
Ryan, if you're done reading the rules, you were explaining sort of what you were gonna do. Your process for this, if you walk through that, it's like really useful for people.
my idea for what I'm gonna answer.
And how you're gonna do it.
Okay, so. My neighbor gave me a dish, that's kind of where a lot of this started, and I thought it would be really cool to make an art antenna. And then I also did find. Well, those things. So. I thought, it would be really cool if I take a dish. And take 2 feed points. Horizontal and vertically polarized feed. And make that work. So. You make a feed point. Make an antenna type, right? If you're doing a contest, you probably want to have more gain than me. When you're doing a dish like this, the feed point, you want the BBS to approximately match this angle here. Which means a lot less gain. So like a 3 or 4 element, yeah, you instead of like 1 instead of 4. So what you do, you take this, and you plug it into an online calculator. It'll spit out some dimensions. You can take, pieces of wire, glue them to a piece of wood, at the correct, lengths and spacings that they say online. You print something, you can do whatever you want. there's a lot of instructions online for how to build that, like, you guys have. Everyone has it. So, follow on something like that, and then.
Could also make a reflector out of like a Mylar sheet,
Yeah, you
stuff
can
like
make
that,
that
or like a
out of
space blanket.
I mean, probably the easiest thing for me is to just make a Yagi antenna with a lot of elements. They're definitely plenty of diminishing returns, you don't think like 5 or 6 or 7. Something like that. But you do that, and then they'll talk about it probably online where you do it. But when you make a Yagi, you have your capacitive elements or your short ones, however, whatever spacing, they'll tell you the length of each one, spacing between them, it's kind of regular, and then you just turn it experimentally. Then you have your driven element, which is the break in the middle, that's where you can connect your coax, and you have your reflector, which is a little longer. The part we maybe can help people out with if they're building this type of antenna, you have to put a little notch piece between here, it's a tiny short piece of wire that connects them to get the correct impedance there. Which should be measured on the DNA, which we don't have access to. So, have to go stuff with our copy for access. I know a couple of us know how to use DNAs. However, it can be measured. Ask me or Matthew. Or you want to show people? Yeah, in your time. How to match. You can also just like say, screw it. It's good enough. It's not perfectly matched, it just means it conforms to the course.
So yeah, just for record, typically they're 75 ohms base, so you're trying to match up to 50 ohms. Not terrible, but you know, it's not great. But it's not terrible, like a folded dipole will bring you up to 300 ohms versus 75 ohms, but you don't need, I believe, the cable there because it's grows back on itself, but you need a balance, but that's the side.
The research, really good resources online, one search away. Look up any one of these antenna types and calculate or design, and you type in the frequencies you want, and give you outputs and all the measurements.
Other questions?
Something that looks cool and just try to build basically is idea.
Which professor did you say you wrote a book on?
Professor, I am naive. I think so, yeah. No, I can show it. I'm not gonna want to show it. I got us somewhere. There are resources out there. We are all students. We know. But I can show you. Alright. Other questions? Alright, anything to say to the YouTube followers out there?
Before we close it,
Make sure to like.
Make sure you like, subscribe, and comment on the video. Yo, boy. Alright.
Yeah.
definitely bio. I know.